Okay. Yes, my talk today is about residual stresses. An overview, really an overview of residual stresses that arise in welded joints and additive manufacturing components. So I go through these topics. I will start with an introductions, giving you probably the definition of residual stress that you already know. But anyway, this is more an academic lessons or an academic presentation that a presentation like that of my colleague and friend Filippo, that is a research linked to research topics. Then I will go through the origin of residual stresses, the effect of residual stresses, assessment and mitigating action that we can operate in order to reduce the detrimental effect of residual stresses when they are positive near the surface of the components. Okay, this is the definitions and a definition of residual stresses. And the residual stress is a self-balanced stress field that arises in components when they are subject to a non-uniform plastic deformation through the cross sections. And this non-uniform plastic deformation is induced in a lot of cases by, let me say, the process, like, for example, welding and additive manufacturing, which we have thermal gradients, high thermal gradients that induce thermal and plastic deformations. And manufacturing processes like, for example, rolling, stamping, or forging process, in which we have an external load that deform and induce a plastic, non-uniform plastic deformation to the cross into the component, and inducing, of course, the residual stress field. So, as I told you before, we have the residual stress may induce detrimental effects. Of course, if they are positive tensile stresses in near the surface of the component, where the crack starts in most of the cases in structural components. Yeah, we have a different kind of residual stresses. More in detail, we have we may consider a different kind according to the scale we are investigating residual stresses. So we have the residual stress type 1 that are in the macro scales, that are most studied ones, and then we have residual stresses type 2 that are in the mesoscale of investigations, and these are residual stresses arising when we have, for example, a precipitation of a secondary phase, or in general a solid state transformation, such as the transformation from austenite to martensite or austenite to bainite and so on, because we have a difference, a variation in a specific volume. So this variation, this mismatch, induce a residual stress inside the bulk of the components. Then we have the residual stress type 3, that is in a micro scale or atomic scale, as you can see in this sketch, in this schematic. And these residual stress are induced by atomic atoms, or such as defects, atomic defects, such as a vacancy or interstitials that induce a distortion in the lattice of the structures of the component. This is in your left. There is an interesting figure that show you the different scale and the result that can emerge from the studies or the investigation, the different scale of residual stresses. If you consider, for example, a cross section XX in this picture, so you can see type 1, type 2, and type 3. In general, we can say that in welding processing and in additive manufacturing processing, we have very high thermal gradients that induce high plastic deformation, non-uniform plastic deformations, thermal deformations. So in general, we observe residual stresses that approach the yield stress or really reach the yield stress of the materials. Moreover, this residual stress may induce a very high distortion during the process itself that can, in some cases, can stop the process itself because of the large distortions in both, above all, if we are considering additive manufacturing processing. So let me spend a few words regarding how the residual stresses in welding arise. I prepared this schematics view in which you can see a butt welded joint, very simple, very butt welded joint, of course, so the cross section of butt welded joint immediately after welding. So we have a central part that is the beam, the weld beam, in which we have a hot part, and the material is heated up to the melting temperature. So the material immediately after welding in this part tend to expand because of the thermal expansion. But of course, because the constraint induced by the non-heat affected materials, this hot part is undergoes to compressive thermal stresses. On the other hand, the other two parts, because the residual stress field is a self-balanced field, the other part is subject to tensile thermal stresses. If, for example, we assume that after cooling, the central part, the weld beam, is can varies in his volumes without constraint, we have a variation, of course, during cooling of the specific volumes of the melted part, because for different reasons. First of all, because we have a contraction, thermal contraction, but we have also the possibility to have an expansion because of the solid state phase transformation. So in general, the competition between the thermal contraction and the expansion induced by solid state phase transformation depends on the materials, on the phase that precipitate during cooling. But if, for example, okay, the central part is allowed to move, to change its volume without constraint, no residual stress appears, of course. On the other hand, because the central part is constrained by the two boundaries of this schematic, this constraint, if is not allowed, and if we have a variation in the volume because the contractions of the thermal part, the central part, sorry, this induce tensile residual stresses near the bead, the weld bead. And as you can see, the values of such a tensile residual stress may approach the yield stress of the materials. When we are considering how the residual stress develops in additive manufacturing components, we have also the possibility to explain that using a simple schematic, as you can see in the part of these pictures, in which you can see that the last layer that is a melted layer during additive manufacturing, because of its expansions, tend to undergo to compressive stresses. But then when you try to cool down to ambient temperature, room temperature, it is subject to compressive stresses because the constraint induced by the substrate. Of course, this is very simple, but the real things are very different in reality. We have different, the phenomenon is very complex, much more complex in reality. For different reasons, I try to summarize these ones. First of all, each layer is not uniformly heated. You know that the heating stage depends on for example, the scan strategy, the raster strategy, and process parameter, of course. Then the real non-uniform temperature distribution over the actual layer will depend on the scan raster strategy, and this induces a non-uniform distribution of residual stress. Of course, as I wrote, it will induce an isotropic, residual stress distribution because of this effect. And then the residual stress at each layer will be influenced by the subsequent layer deposition. So you can imagine that at each point of the additive manufacturing components, the thermal-metallurgical history is very complex and very long compared to what happens in a welded joint, for example. So it is a very complex phenomenon. As I told you before, the effect of residual stresses in general, or in this case for welded joints, may be positive or negative, depending on the scene of the stress field near the surface of the component or near the weld toe of a welded joint, of course, where the crack starts in general, where the crack starts. The residual stress negatively affects the structural integrity of the component when they are tensile in seam, because they tend to brittle fractures, because they reduce the stress corrosion cracking resistance, but in my opinion, above all, because they reduce the fatigue strength of a component in the high fatigue cycle regime. That is, in my opinion, the most important effect of residual stresses. By focusing on these facts, the effects of residual stresses on the welded joint and fatigue strength of welded joint, we have different findings with different outcomes. First of all, it is important to observe that if we have a high tensile residual stress in welded joints, the fatigue strength of welded joints is independent on the mean stress, the applied mean stress to the joint itself. You can see a schematic in the left side of this picture, and also the SN curve, the fatigue curve of this welded joint with this geometry. You can see that the fatigue strength is almost independent on the mean applied load. Another effect of residual stresses is that, according to this thing, of course, they can reduce the fatigue strength or improve the fatigue strength of welded joint in the high cycle fatigue regime. These are two experimental evidence. The graph in your left and also in your right, in terms of the applied load or the strain energy density. And how can we explain this phenomenon? We try to investigate the residual stress field very close to the welded toe, and when we simplify the weld toe as a sharpening notch, as you can see in these pictures, it is interesting to observe that the residual stress is characterized by asymptotic distribution, like in welded joint when we applied an external load, as already observed by different working literature by Professor Lazzarini, Professor Berto, and firstly by Williams. So also the residual stresses has this behavior. This are characterized by this kind of field, which is an asymptotic or singular stress field, that can be, of course, represented by the well-known equation by Williams, and which in a log-log plot, it can be represented by straight line with a slope that is given by the grade of the singularity, here defined by this potential that is 1 minus lambda, where lambda is the aging factions of aging values of the solution by Williams. Okay, knowing that, with this finding in mind, we can also investigate how the residual stress influences the fatigue strength in the high cycle fatigue regimen, because we can operate using the superposition principle. And if you consider, for example, low external applied loads, such as in this case, this is a work in which we investigate this kind of joint, aluminum alloys. We applied this kind of external load, 25 megapascal. We are a high cycle fatigue regimen. And we found the different values of the notch stress intensity factors in the stress relief state compared to the as welded state. So we can see that is this difference that can change the strength of the joint in the high cycle fatigue regimen. On the opposite side, if we apply a very high load, external load for the aluminum alloy, in this case 120 megapascal, you can see that because of the plasticity effects, we have that the two stress distribution near the weld toe are almost the same. That is and this means that, of course, in this case, we have no difference in the fatigue strength of welded joint in the low cycle fatigue regimen, of course. So we have defined an equation that can use in order to quantify these effects in the high cycle fatigue regimen. This is this equation with this formula, in which K1 is the residual notch stress intensity factor we found. Let me consider now the effect of residual stresses in additively manufacturing components. We have, in general, three advantages, three drawbacks when we consider residual stress in component. Residual stress, first of all, influence the crack propagation in additively manufacturing components that improve the speed of the crack because of tensile residual stresses. Then the second detrimental effect is that we have a distortion once we remove the component from the constraining base plate. And finally, during the process itself, residual stress can induce, or thermal stress in this case, can induce deformations of the components during the process itself that can stop or fail the process itself, as you can see in the schematic in the figure C in your right in this picture. Now I want to spend some words about the techniques that we can use for measure residual stresses. I classify these techniques in into three categories: destructive, semi-destructive, and non-destructive techniques. So some of these destructive techniques can be the contour methods and slating that are quite similar to the first one, the contour method. In this case, we need to destroy the component. In this case, for example, plates, have to cut, really to cut the plates. And according to the deformation in the surface where we have operated the cuts, according to the deformation, we need to apply an external tensile or stress, sorry, in general, stress distribution in order to produce the first cutting surface, in order to return the cutting surface to its original position, really. Doing that, we are able to evaluate the residual stress that we have in the component across all the section and over all the surface where we have operated cuts. Of course, this stress field we applied will be with an opposite sign compared to the real residual stress we have in the reality in the component. Then we have semi-destructive techniques. They are already well known. I mentioned the deep hole drilling technique or the ring coring according to the geometry of the hole that we need to operate. In any case, we use strain gauges in order to assess, to measure the deformation of the material during the hole drilling, sorry. And according to this measuring, we are able to assess the values of residual stresses in the component. Finally, we have the non-destructive techniques. All of them are based on the Bragg law, and all of them use a beam in order to calculate the spacing between a lattice, using, of course, the Bragg law. And according to the energy of the beam, for example, we have the neutron diffraction, synchrotron X-ray diffraction, X-ray diffraction simply, sorry. According to the energy of the beam, we can assess the residual stresses at the different depths of the component. So, for example, for using X-ray diffraction, we can measure residual stress only in the surface of the component or very close to the surface of the components. On the other hand, using neutron diffraction, we can assess the residual stress more in depth. About the assessment of residual stress, we have another possibility. We have the possibility to use the numerical modeling. This is one of my principal topic I'm involved to. And of course, using welding simulation, we are able to have a knowledge of the residual stress in overall the components, in all the geometry of the component, not only in single parts, as we can operate using experimental techniques. Of course, but when we are when our goal is to assess residual stress, we need to operate using some simplification in our numerical modeling. In particular, when we try to model welding operation, we need to use the computational welding mechanics techniques. Let me consider this simplification. First of all, we have to simulate the thermal metallurgical loads induced by the welding during the first part. So the first part of the simulation is the calculation of the thermal field, or better, the metallurgical thermal history at each node of the component. And then we use this thermal history at each node as inputs for the calculation of the thermal and residual stress into the components. In this way, we operate using an uncoupled thermomechanical analysis, and in this way, we have no we have advantage to avoid the simulation of fluid dynamics calculation or fluid dynamic phenomena. Sorry. We can use numerical simulation for the computation of residual stresses in additively manufactured components. Well, but you can observe that is very expensive, more expensive in this case compared to welding simulation, because we have to simulate the melting of hundreds and sometimes thousands of layers. Each one by means of laser scanning strategy, they can change from layer to layer. So we have to consider this effect as well. And of course, as in welding simulation, the thermal and metallurgical history node is applied to the model for the as input for the calculation of the transient elastoplastic mechanical analysis. Okay. Because of that, it is imperative, mandatory for simulation of additive manufacturing process when the goal is to assess the residual stress to use numerical strategies. I try to collect these ones in these pictures. So first of all, if you are interested only in assessment of residual stress only in one layer, of course, we can simulate only one layer and have a very important information focusing only on one layer. In this case, we're able also to assess the distributions of residual stress and the effect of the scan strategy and so on. So using one layer, we have the possibility to study the effect of the laser or the beam movement. So the effect of this movement on residual stress, of course. Another simplification when we have to simulate the entire components is to consider groups of layers. So we have to merge some layer to each other and to simulate group of layers. We have also the possibility to using the refining, coarsening of the mesh that is refined close to the beam during the simulation, and this portion of the mesh follow the laser source of the beam source, reducing the elements required for the simulation, of course. And we can also to deposit a single tract instantaneously at the same time without considering the effect of the velocity of the speed of the source. And of course, we have the possibility to simulate the position of a single layer simultaneously. Sorry, without in this case, without considering the effect of a scan strategy used for the deposition of this layer, of course. According to mitigating action that we can operate in order to reduce the residual stress in general in welded in additive manufacturing components, I can mention to the use on appropriate manufacturing design, of course, first of all. Then we can optimize the process parameters in order to reduce the thermal gradient, if possible. And we can use post-welding heat treatments of a post-welding heat treatment. Also, in additive manufacturing components, And we can also use mechanical strategies such as shock peening, teeth dressing, vibration, or in this case apply to welded joints in order to reduce or change, switching from the tensile stress to compressive stress near the weld toe, and in this way to improve the fatigue strength of welded joints. Shock peening can be operated also, of course, in additive manufacturing components. Let me promote this book that was published last year by myself and my colleague and friend Filippo Berto. It is a book that collects some works, interesting works about numerical simulation of welding joint experiments, residual stress assessments by experiments in welded joints. Okay, this was my contact. This is me when I was a little bit fat. I finished my presentation, so I here for you for a question. Thank you very much.
Thank you, Paolo, for this excellent overview of very important problem in welding. And now I invite participants to ask a question, if any. If there is no question, I will make a short comment, but I need a file to open. Just give me a few seconds. Then I need to share the screen.
My screen or your screen? Sorry.
Please close your.
Okay. Close my. Okay.
Yes, please.
Okay.
Now I will share mine. So what I wanted to show to everybody is a draft program of a TC1 meeting. So we have another TC which we can work with. It was in September this year, online, unfortunately. This is a technical committee on elastic plastic fracture mechanics. Uwe Zerbst is one of two chairmen, and you can see here the list of lectures that were provided. And I just wanted to everybody to understand that everybody understands how important this problem is. Especially interesting was, from practical point of view, this Isabel Hadley from the Welding Institute in Cambridge and her presentation of development of BS 7910 and R6 procedures. I think we know what it is about, but now residual stresses are built in some way, and then a couple of other very interesting presentations. I don't know if we will have any published trace afterwards, but we will certainly work on it. So TC1, which is basically an elastic plastic fracture mechanics, in this case was devoted completely to the topic that Paolo Ferro just presented us. So it is definitely a hot topic, and Paolo, once again, thank you very much.
You're welcome.